Hello, ladies and gentlemen. We are back in chapter 6, learning about circles, and we're going to start out with the segment relationships in circles section. We want to find the lengths of segments formed by lines that intersect circles and use the lengths of segments in circles to solve problems. You can pause the video if you'd like to read the vocabulary and essential questions, but we're going to go ahead and get right into the warm-up question. And what we see we have is a proportion on number 1. So we remember how to solve a proportion from our pre-algebra days. And we have 35x is equal to 5 times 28, which ends up being 140, which is equal to 35x. And then we know that x is going to be equal to 140 divided by 35, which is 4. Final answer. We'll take a look at number 2, and on number 2 we are tempted to divide both sides by 3, but if we do that we need to still follow order of operations first, and that means that x is going to be equal to 12 squared over 3, or 144 over 3. So power comes before division. Once we raise 12 to the second power, then we can divide by 3, and that's going to give us 48. Again, this is our final answer. We'll take a look at number 3, and number 3 is involving this diagram. It says segments BC and DC are tangent to circle A, and we want to find the measure of segment BC. So what we are going to do is notice that when we have tangents, we know that they are congruent to one another. So BC is congruent to segment DC or CD, and that means that the lengths are equal. So we'll plug right in for the expressions that were given in this question, and then we're going to solve. So 5y minus 3y is equal to 5 plus 1. 2y is equal to 6, and that means that x is equal to 3. We wanted to find the length of segment BC. So BC is equal to 5y minus 1. We plug in what we just found, which is 3. That means BC is equal to 15 minus 1, or 14. Okay, we've got a theorem next, Theorem 12-6-1, and it is called the chord-chord product theorem. You can see that we've got two chords, CD and segment AB, and this theorem says if two chords intersect in the interior of a circle, then the products, meaning multiplication, of the lengths of the segments of the chords are equal. So what this is saying is if we multiply this to this and this to this, those products are going to be equal to each other. This is going to allow us to do some problem solving. So let's take a look at example number 1. All right, on example number 1, we're going to use this circle, and it says find the value of x and the length of each chord. Now we just said we know that we can multiply this times this, and it's going to equal this times this. All right, so that means EJ times JF is going to be equal to GJ times JH. And we'll go ahead and plug in the values that we have for both of those expressions. So EJ is 10 long, JF is 7 long, and that's going to give us, of course, 70. GJ is 14, and JH is x, so 14x. And so this means that x is equal to 70 over 14, or 5. Now, the length of each of the chords, the one in red, of course, is 14 plus x, so GH is 14 plus x, which is 5, or 19. And then the other chord, which is FE, or EF, is equal to 7 plus 10, which is 17. Okay, let's take a look at example 2. Real world application. The art department is contracted to construct a wooden moon for a play. One of the artists creates a sketch of what it needs to look like by drawing a chord and its perpendicular bisector. Find the diameter of the circle used to draw the outer edge of the moon. So what's going on here is we actually have this moon that keeps going. We just don't see it because the artist has only drawn part of it. Now, what we know is the diameter, which is going to go all the way across the circle. The diameter is going to be equal to D, and that means that this piece is going to be equal to diameter minus 8. So we can look at the diameter as this times this. We saw that it was a perpendicular bisector, and we know that this chord that I'm drawing in right now is 18 inches long. So it's bisected, which means that we have two 9-inch segments. So we have 9 inches there and 9 inches there. What this means is we can set up an equation where we say 8 times D minus 8, which are the red, is equal to, and now we're going to deal with the blue, 9 times 9. So we can multiply this to get 81, and then we know if we divide both sides by 8, then we have D minus 8 is equal to 81 over 8, and D is equal to 81 over 8 plus 8, which if we put into the calculator is 18.125, and that, if we convert it into a fraction, is 18 1/8 inches. And that is how long the diameter of the circle is. So we have a couple new definitions. A secant segment is a segment of a secant with at least one endpoint on the circle. So the secant segment PN is one. NM, KM, and JM are all secant segments of this circle. And we also have something called an external secant segment, which is a secant segment that lies in the exterior of the circle with one endpoint on the circle. And of course, that is an example, these two segments that are outside. So we have a theorem associated with the secant segment that we were just talking about, and it's called the secant-secant product theorem. And what this says is if two secants intersect in the exterior of the circle, like at point E right here, then the product of the lengths of one secant segment and its external segment equals the product of the length of the other secant segment and its external segment. So that sounds a little bit complicated, but basically all that's happening is we have the whole times the outside is equal to the whole times the outside. So the whole times the outside is equal to the whole times the outside. Okay, so we're going to use that for some problem solving, and we'll take a look at the next page. On example number 3, I'm going to add some points in just to make it a little bit clearer what's going on. So right here, let's see, we'll put it in pen. Right here we'll call this point F, and we'll call this one point H. Okay? So remember, it's whole times part equals whole times part. So GE is the whole, and that times FE is going to be equal to GH times HE. So let's put that in. All right, we'll substitute in the values. For GE, we know it's x plus 8. For FE, it's 8, and that's going to be equal to DE, which we can call that 16, 9 plus 7, 16 times HE, which is 7. So what I'm going to do is divide both sides by 8, just to simplify the math a little bit. So on the left-hand side, we're going to have x plus 8, because the 8s are going to cancel. On the right-hand side, we're going to have a 2 left over, and that's going to be 2 times 7, because 8 goes into 16 twice. And that means that we're going to have x is equal to 14 minus 8, or x is equal to 6. Now, we needed to find the value of x, but we also need to find the value of, or the length of each of the secant segments, and that means GE, which is equal to x plus 8, or 14, and then of course DE, which is equal to 9 plus 7, or 16. And those are all of our answers for that question. We have something called a tangent segment, which is a segment of a tangent with one endpoint on the circle. So segment AB and segment AC are tangent segments. And we have, of course, a theorem about those. 12-6-3 says, if a secant and a tangent intersect in the exterior of a circle, then the product of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. Oh my goodness, what does that mean? That just means this times this equals this squared. That's it. So we will be able to carry that through in example number 4. And so you can see we have a secant-tangent type situation. Now, we know that ML times JL is going to be equal to KL squared. So let's set it up that way. And we'll go ahead and substitute in. And ML is 15 plus 5. JL is 5. And that needs to be equal to KL, which is x squared. So we have 20 times 5, which is equal to 100. And that means that x is equal to 10. And that's what we were asked to find is the value of x. And that brings us to our IP. So go ahead and get going on that. Good luck, and I'll see you in class.